Hello, everyone, and welcome to Coffee with Caleffi. We are going to get started here right at the top of the hour. So I'll go ahead and start going through the first few slides here, and then we'll bring in our guest. So the topic today is proven plumbing systems from both sides of the flange with Brent Cunningham. And this is a continuation for a little bit of backstory of an in-person and virtual series that we've been doing with Grundfos over the course of the year. So this will be the heating version of a plumbing topic that we've done before in coordination with Grundfos. So I'll get started with a couple housekeeping things. If you are having issues with the audio, generally the case is log out and log back in, and that sorts it out for most attendees. If you are having issues with the audio, you can call GoToWebinar support directly. If you want a copy of the presentation, hit yes in the post-webinar survey. And then we'll also have this up on YouTube in a few days if you want to, if you have to duck out a little bit early and want to come back and watch the rest of it a little bit later, since this is an hour-and-a-half version today as well. Okay, if you are someone who likes certificates of attendance, we'll send you one with 1.5 PDHs. Some states accept these, some states require something specific to the credentialing in Wisconsin as an example. So hopefully this works for some of you out there, but we're happy to send the certificate with the description and the agenda items and things like that that are pretty universal. Then we have a big announcement today. So one of the things that we've been proud of kind of over the course of the last few years at Caleffi is AHR, the ASHRAE trade show that's every year in January or the first week of February. They have a whole different set of things that they do early for product-specific awards. So we enter products for these every year. We've had a great run, 18, 19, 20, 21, 22, with some finalists and a win for the angle mix in this category. So we are, as of midnight tonight, able to say that the 2023 plumbing category winner is the Caleffi 536 series Prescal HP piston style pressure reducing valve. So this is kind of breaking news today. You'll see some more information about this directly from AHR, and it was in the ASHRAE newsletter that goes out to their whole membership today. So really excited about that. We'll definitely be communicating more about this, but this is kind of the first crack that we get to say anything to the public. So we're excited about this product and the capabilities it has for high pressure applications. Could be a high rise, could be a commercial laundromat that takes a lot of water hammer damage to traditional style pressure reducing valves. This valve is going to work really well in those applications, but more on that later. The other things that we have kind of related to this topic, the last issue of Hydronics that was Hydronics related was issue 30. So that was Hydronics for low energy and net zero buildings. So that one is kind of a bigger picture view of some of the things that we'll talk about today with circulation and separation. That's up on the website as always. You can find it at hydronics.caleffi.com. And then the most recent version is about pressure reducing valves. So that's going to talk about the 536 valve that won the award this year as well. Okay, next month, we're going to have returning champion John Siegenthaler is going to talk about kind of a unique application that I think has a lot of room to run in big warehouse type applications where you have an air to water heat pump with or without a buffer tank. So John will kind of describe when and how you might be able to just take that energy and put it right into the slab. That'll be a cool topic that I think, as all these Amazon warehouses and things are popping up all over the world, there are just a lot of places where this could be a great fit. Okay, and today we have our guest presenter is Brent Cunningham. He works at Grundfos. He's on the OEM side, so we work with him a lot for the parts that we kind of go back and forth with as manufacturers. And he's going to walk us through this hydronics topic today from the the business development side of Grundfos. So welcome, Brent.
Thanks, Max. Good afternoon to you, and congratulations to Caleffi. You guys are always finding ways to innovate with the new PRV award. That's great.
Yeah, you guys too. So we'll get to that. You guys have kind of breaking news as well that we'll talk about at the end of the presentation. So to get started, here's kind of what we're talking about today. We're going to go through some of the kind of why we did this series thing to start with, and then we'll go through the other agenda items here. Kind of first technical topic will be Brent talking about the circulator. So taking a little bit of a step back, this is the slide template that we used when we did this presentation in person with the perfect loop. So what we wanted to start with there, as well as what we'll do today, is why hydronics? Why is this even something that we want to talk about? So to start with, water is just the best way to move energy around, I think. So if you're going to take a BTU from point A to point B, water or a fluid with water and glycol or something like that, it's just a really good way to transfer energy around the building. So as well as low temp hydronic systems are going to be kind of the future proof ready systems that we want to move into the next phase of whatever hydronics is. So low temp hydronics give us the ability to adapt to all sorts of different energy sources, whether it's a gas boiler or some electric device in the future. We just have the options and can set everybody up for success with low temp systems, and we can adapt to those as well. And that's another issue of hydronics that we have, that it's one of my favorites. So if we're going to future-proof the mechanical room, a low-temp hydronic system is just going to be the way to do it. That's going to be our best foot forward. So to start with, we're going to do circulator sizing. So I'm going to turn this over to Brent. I'll toggle my camera off for a few slides here, and then we'll kind of come back and go back and forth as the presentation goes on. So just cue me as you want me to move through these, Brent.
That sounds good. And, these are some of the topics that we went over, like you said, with the in-person training for contractors. And one of the biggest requests we get for just basic training for understanding pumps is how to size and select a circulator. Whether it's contractors, installers, people that do troubleshooting, engineers, they just want to know how to select a pump. So you need to understand how to read a pump curve. You need to understand how to size your loop, and how to understand what's going on in your loop that the pump is adapting to. So the topics we kind of talk about here with the basics is understanding your pipe loops, including velocity, how to select a pump, and we're looking at duty points with flow and head, as well as the system curves and how that adapts to and how that coordinates with some different pump curve options. So also flow and heat transfer. So the reason why we're moving water around for a heat system is to deliver BTUs. Variable speed pumping is an area where this will, I think, is going to be the future with heating. So we still have to start with understanding the basics with fixed speed pumping, and then we can move on to the variable speed pumping. So we'll talk about that as well, and what's coming next with Grundfos. So let's advance forward here, Max. So in a hydronic system, in a heating loop, what does a circulator pump do? And we'll talk about what it does not do. So essentially, it's a centrifugal pump that's a differential pressure device. So it's creating differential pressure. And the whole reason it's creating differential pressure is to have enough pressure to overcome the friction losses in the loop. So if we look at the pump on the diagram, and we kind of have a triangle with an arrow. So going from the pump to the left, that's going to be the highest pressure point. Pressure in the system is right after the discharge of the pump. And as we follow the loop around, going through the straight pipe and elbows and valves, going around the loop, kind of clockwise there, it's losing its pressure through friction loss through the internal pieces of all the pipe, valves, and fittings. So really, it's creating pressure to overcome all that friction loss, and it's creating flow by doing that. So when we're looking at, is it the right pump for the loop, we want to make sure that it can overcome the friction losses in that loop and create enough flow to give the right BTUs and the right heat transfer for what you need. So this is a closed loop. We don't have to worry about elevation head. This is not a booster pump where we have to take into consideration what's the elevation of the loop. So if it's a 2-story house, we don't have to say, okay, well, that's 20 feet or 16 feet of extra elevation that we need to add into our total dynamic head. We're just looking at calculating the friction head, so we don't need to worry about elevation. Just circulating the water around that loop. So let's advance on to the next piece. So how do we select a circulator pump? And there's a right way, and I think, I don't want to say a wrong way, but the right way of going about it is to really understand if it's the right pump for the loop, whether this is a new construction or whether it's a replacement situation. I think this is the right procedure, is determining what is your target flow. And when we do that, no, let's keep advancing there, Max. We have some more information. So we're going to determine the target flow, and we get that flow information not from the pump, but what's the equipment that we're pumping for? Is it a boiler? Is it a heat pump? What's required? What does their equipment guide say of what flow we need? That's step one. And then we take that flow and we calculate the pressure drop of the loop at the flow, and we're going to take that flow, we're going to take that friction head, creating a duty point, and that's going to create a system curve for us. So then we just match that system curve with a pump curve, and you can do that with data books, or you can just plug in the flow and head into software, selecting what you need. But the right way of going about it is selecting flow and figuring out what's that pressure drop of your loop at that flow. So let's advance to the next piece. In a retrofit application, replacing like for like is what happens in a lot of situations where they just say, okay, this is the circulator that was there before. I'll put the exact same pump in. If I can't get the exact same pump, I'll just match the pump curves. And, we get a lot of times, well, I have a 3/4 horsepower pump. Give me your 3/4 horsepower pump. And, the problem with doing that is not all 3/4 horsepower pumps have the same performance. There's different efficiencies, different performance curves. There's flat curves, there's steep curves. So that's not really the right way of going about it. So, from a replacement standpoint, replace an existing pump like for like without analyzing the system's needs, we say is kind of like a doctor prescribing the same medicine for a patient, only because that's what the last doctor did. So you probably don't want that for your healthcare, and you don't want to do that for your diagnostics of your system. So you're assuming the last installer had the right pump selection and that they knew what they're doing. And then you're taking that responsibility, carrying that forward. So you can advance a little bit there, Max. But, we wouldn't do the same thing with replacing a boiler. When you're changing out a boiler, you probably want to do your heat load calculation and see what your heat loss is and make sure that what you're putting in is the right thing for the home and the right thing for the system that it's connected with. So no different than replacing for a pump. So determining the target flow, we're just going to reference other data. So we have a boiler manual kind of chart here, or you could be looking for zone sizing. You could be looking at your heat emitters and looking at what kind of BTUs you need, what kind of corresponding flow. So looking at this chart, I mean, we see this in all the equipment guides, is they have the different equipment models on the left. And then let's just take a look at the 125 model, and we take our eyes to the right, we look at the gray area. We say for that model, we're needing 10 gallons a minute for that model is what the equipment manufacturer is saying. And that gives us a 20-degree temperature rise on top there. So if we had in our system, if we actually had 8 gallons a minute for that same model, that's to the right. We're going to actually have a 25-degree rise when we do that. And this also shows us the head loss through the heat exchanger and the components as well. But there's a lot of data in this sheet telling you, depending on temperature rise, you would have a different flow. So again, that same model, the 125, if we were a 15-degree rise, we'd have about a little over 13 gallons a minute for that. But okay, so we've determined the target flow, and now we need to look at the pressure drop of the loop. So let's go to the next slide. So again, we're gonna take a look at our loop. We're gonna count for all the components in that loop, and it just doesn't take hours to do. And again, if it's a retrofit situation, it could be a little bit harder because you have to do a little bit of guesswork with things behind walls. Obviously, if it's a new construction or a new build, we have our Excel spreadsheet with the complete list of all of the components and piping. So if it's a retrofit situation, we can take some liberties, and we can be off by a few elbows, a few T's here and there, but we want to do our best to have the right kind of accounting for the loop. So this process allows us to help visualize the water's pathway, and it's going to give us an equivalent equivalent feet in the loop for each pipe diameter. So what we do is we take that equivalent feet and we can put it in software, or we can just reference a table, and that's going to give us our pressure drop. That's going to give us our friction head loss. So let's take a look at the next slide as an example here. So the same diagram here, except for we've accounted for all of our, is all 3/4 inch copper and fitting. So we have about 58 feet of straight pipe. We've accounted for elbows, T's, and some other valves. So what this is saying with the elbows is for every elbow, it's equivalent to 2 feet of straight pipe, equivalent friction head loss. So in this example, in that loop, we've accounted for all those T's and elbows you see, and we have about a little over 100 feet. So that's our equivalent feet, and now we need to reference a chart like this that we can take a look at what's the actual friction head loss at a given, our equivalent feet. So it just happened to be that our example lines up nicely, equivalent feet of 100. And if we take a look at like 3 gallons a minute on the left that we have circled, and we're going to take our eyes over to the L copper section, and we see our head loss is about 2.91. So just call it 3 feet ahead at 3 gallons a minute for that 100 feet. Now, if we look down a little bit further at 5 gallons a minute through that 3/4 inch loop, we're about 7 feet ahead, is how you read that. Now, what if I'm not exactly 100 feet ahead? Well, you just have to do a little bit of math. If we were 150 feet or 200 feet, so let's just say 200 equivalent feet at the 5 gallons a minute, we would just take that 7.11, take that times 2, and at 200 equivalent feet, we'd have 14 foot of head loss. If we were 150 feet, we just take that same number, 1.5, 7 times the 1.5, about 10 feet of head loss at the 5 gallons a minute mark. So equivalent feet, that's just the accounting piece to get our head loss. So one of the things we haven't talked about is the line, the column of velocity. So that's an important piece. The head loss kind of helps us with our duty point, but what we want to keep in mind at a given flow for a given diameter pipe is we kind of want to stay within some boundaries of velocity. So 2 to 4 feet per second is what we say in the industry. If we were trying to push 10 gallons a minute through that 3/4 inch pipe, you can see in the velocity section there, that's around 6.6 feet per second. So that's moving pretty quick through a 3/4 inch pipe. So it can do it, but there's going to be some consequences of that. So what I like to do, and we'll advance to the next slide, I like to kind of have a quick sheet with some velocities. And, I'm just showing some L copper here. You might want to have M copper, whatever you're used to dealing with your systems. You can put some PEX there, just kind of as a quick guide, a quick sheet of your boundaries of 2 feet per second and 4 feet per second. So we kind of want to stay within that. So on the 3/4 inch pipe on L copper, you probably should stay between the 3 to 6 gallons per minute through that pipe. So if we're too slow, water's not going to pick up the excess air, which is a problem. And then if we're too fast, we're going to get the velocity, we're going to get pipe erosion, and we're going to get noise if the water's flowing too fast through there. So just having kind of a quick guide at hand is not a bad thing. Some people have these memorized because they're in mechanical rooms every day, and just knowing that, oh, okay, for a 1-inch pipe, I want to be 5 to 11 gallons a minute, just as a kind of quick guide for themselves. It's not a bad thing to keep to memory, especially if you're working with the exact same, M copper or Schedule 40 steel pipe or something like that all the time. Let's advance to the next slide here. So finally, we're to a pump curve. So we're talking about understanding our flow, understanding our pressure drop to get to our duty point. But we're gonna have to match that to a pump curve that looks like this. So we do have head on the vertical y-axis, or that's our differential pressure of the pump. And then on the bottom x-axis, we have our flow. So where the pump is going to perform is on that blue line. And where we want to perform on it is going to be the middle third of the curve. So what we're targeting is that our duty point and the corresponding system curve is going to land somewhere in that shaded red area in the middle. That's what we're hoping for. So every manufacturer has a best efficiency point that's published, and then the Hydraulic Institute, gives out parameters for defining the preferred operating range. So yes, we want to be kind of in that preferred operating range. not only for electrical efficiency, but just longevity of the pump, that if we're operating that area, that's going to make sure that we have a long running pump. Whereas if we're operating near the area on the left near the H, that's shut off head, or if we're on the area on the right near runout, um, we could have unstable flow. We could have excessive vibration. We could have some extra noise. It's not going to be behaving exactly the way we want the pump to behave. So those are just different terms that we have in the industry of shut-off head, of run-out flow. And on the small circulators, you talk about run-out, you can operate it kind of in that area. It's not a good place to target when you're selecting pump. You really don't want to target to be operating there if you can help it, because then if you get in, if you're used to being in small residential jobs, and then you do a light commercial job, and you select a pump in that run out region, um, you're going to have some problems at some higher horsepower with unstable flow and performance. So good to know that. And then also, again, we have feet of head in the vertical column there for our pressure, differential pressure. But it's a good thing in the field and practice to kind of understand that you can convert between metrics between feet of head and PSI. So knowing that 2.31 feet of head is equal to about 1 PSI, that's a calculation I like that I have memorized, that I can kind of convert. You can convert the other way too and say, I think it's 0.433 PSI equals 1 foot of head. I like the math better the other way, and that's just the way I go about it. But so that's a little bit on the pump curves. And now let's select a pump based off of the duty point with the next slide. So here we have our target flow and head. That's the duty point, and that's where the two black lines are intersecting with the little dot. It looks like 5 gallons a minute, about 9 feet ahead. So that's our target. That's our target flow and head, our duty point. But we're only going to operate where the actual system curve meets the pump performance curve. So, and you can see after we put in our flow and head, the system curve was drawn for us in the software, and it actually connects up and it shows us a landing point on our performance curve. So where that is 6 gallons a minute at, I think it's about 13 foot ahead. So that's where we're actually going to be operating. Now, is that really where we want to operate? Is there a problem with that, of overflowing a little bit? And that depends on the loop that you're in and what you're trying to do with that loop. If you need to be precise flow, you're going to need a balancing valve to get to exactly that 5 gallons a minute. And what that does is it creates extra friction loss, and it's going to actually, if you just ride up the curve, you look at 5 gallons a minute, take that black vertical line and go straight up and intersect with the blue pump performance curve. That'll get us to the 5 gallons a minute, but we'll actually be operating at about 17 feet ahead. So it's adding extra pressure to the system to do that, which requires extra energy, and but it does get us dialed into the right flow. But using a balancing valve to get into exactly where we need to be with a fixed speed pump is the way that we've been doing it in the industry for a long, long time. So let's go to the next slide, and it's going to just kind of say about practical situations of, well, the flow and head that we calculated, okay, 5 gallons a minute, we know our flow based off maybe the equipment size. We can be pretty sure that's what we need. But the actual friction loss, a lot of times there's extra buffer, there's extra calculation that's put into there, like a fudge factor, that we have a lot less, or we have a lot more friction head that's put into the calculation than what's maybe needed. So what if in reality, we put the pump into a loop and the actual system curve doesn't look like this? It's a flatter curve, because in reality we're maybe 4 feet ahead. And what that would mean, if we just can kind of visualize that, 4 feet ahead at 5 gallons a minute, different duty point, we don't know that. And what's going to happen is the system curve is going to be way further to the right of where it's going to be performing on the curve. So we're going to be overflowing a lot more if our actual friction losses in the piping loop are less than what we calculated. And that happens a lot. And it's happened a lot in the past, to the point that a lot of longtime pump professionals, their modus operandi, MO, is to select pumps to the left of the duty point. So this one's kind of to the right of the best efficiency point, and they would select to the left of the best efficiency point, because they know there's so much extra buffer factor in the friction head that if they do that, well, there's a good chance that in the field installed, it's going to operate where it needs to be, because we know that systems are designed with too much friction head in the calculation. So that's pretty common practice, that people try to select to the left of the BEP point. Let's continue on. So a little summary on some of the basics is a circulation pump's just creating enough differential pressure. It's to help overcome pipe friction loss and to create enough flow to deliver heat. So keep in mind, every piping loop has a unique loss curve at a given flow. The equivalent pipe length, that's the accounting part to help give us a pressure drop in feet of head. And also our guardrails, let's keep our velocity between 2 to 4 feet per second for good system practice. Also, our pump is only going to operate where the system curve meets the pump curve, so keep that in mind. And finally, target the pump operation for the middle third of the curve, and don't forget that 2.31 feet ahead to the 1 PSI formula. Keep that in mind.
And Brent, as we get to the advanced section here, I want to give a shout out to, I used to work in Colorado, and there's a mechanical contractor, Concept Mechanical in Avon. And at one point we asked them about pump sizing. They say, well, we don't do the pumps yet. We wait until we install it, and then we go back and we measure the fittings. We see, how many feet of pipe did we use, how many fittings did we use, and then we take the spacer out and put the pump in based on that. And that will get you right to the right point on your curve. But like you said, generally you're sizing for what you hope will happen with some sort of fudge factor.
Yes.
But if you wanted to do it, as close to perfect as possible, you count the fittings, you count the components that it's pushing through, and that'll get you right on the number.
Yeah, and they're absolutely right. And there's a lot of creative installers out there that have some good ways of going about it, and if it works and they like doing it, we're not going to stop them from doing that. That's a great idea, and that's awesome that we have installers and contractors out there that are willing to do things like that. So that's pretty cool. So kind of advancing on, so we kind of talked about the basics of how to select a pump, but in the field, there's some basic diagnostic things we can do based off of differential pressure, based off of differential temperature, just to understand what is the system doing right now. So we'll talk about that. We'll talk about flow and a little bit of heat transfer. Then also we're going to get into how does pump operate when we have a zone valve system, and then we'll get into the variable speed side. So let's get started with this section. So let's say you go into a mechanical room, you inherited someone else's job, and we think there's a pump problem. We don't think the pump is performing the way it should. And of course, we're a pump manufacturer, so sometimes we get blamed for your pump's not performing properly. And the basic test we can do is we can measure differential pressure at the pump. We can see, does it have the right shutoff head to match the published pump curves? That's a starting point. And then how is it operating in the field? And a lot of times this is with fixed speed pumps that you don't have an electronic display readout to tell you where it's performing. You can measure the amps, you can measure the differential pressure, and you can maybe measure the temperature if it's overheat. But there's not a lot we can do except for infer what the flow is, unless you have a flow meter that tells you what the flow is, or a flow readout. We have to calculate what the flow is and determine where it's operating on its curve. So the way to do that is we got to find the pump curve of the installed pump, and then we need to look at differential pressure as we show here. And we need to do that at a closed valve and then fully open for normal operation. And just, are we getting the right flow? So let's go to the next slide so we can kind of visualize what that would look like. So we would start off by saying, okay, this is the pump curves that we have. We believe we're running, confirm that you're running on the right speed. So the 3 blue lines there, that's a low, medium, and high speed pump curve. So you'd have a toggle switch at the pump, and we would just determine where we're at. And you can see, remember, our 2.31 feet ahead for 1 PSI, the shutoff head for the max curve, 19.2 feet ahead. So that's going to be about 8.3 PSI. So what we'd want to do is actually literally shut off on the discharge side, shut off the valve there, and see what our pressure is, and convert that to feet ahead to see if we're matching up with the curve properly. So the next step, we open that valve on the discharge side, let it run in its normal operation, and see if that matches. Well, first of all, we have to plot it. So let's just say that we're at 11.5 feet. We have to, or we measured 5 psi. We calculate that that's actually 11.5 feet. So we plot that, and you just go to the right and say that's where we land on the pump curve, and you just come straight down, and it shows we're about 7.5 gallons per minute is where we're operating at. Is that where we thought we were going to be, and is that a problem? Now, typically, this is where we bow out and we say, oh, okay, so the pump's operating normally, it's operating on the curve where it should be, and a lot of times we come in the process at this point, but we didn't select it for you, so let's try to select the right pump and see what we can do if it was on part of the curve that was not good. So right where it's at here that we show is great, it's perfect, but maybe your target was you didn't think there was going to be so much head, you thought there was going to be less friction head, and it was going to operate further to the right on the curve and deliver more flow. That is a possibility. So it's just something you can do in the field as a troubleshooting thing to dial in your system and understand your system of how the pump is interacting with the pipe loop. So let's go to the next piece where we talk about flow. So the reason why the circulators exist for heating systems is to deliver BTUs through flow. And a lot of people have seen this simplified heat formula, and we look at it, it says flow in gallons per minute equals BTU over a constant of 10,000. So a simplified way of thinking about this is, okay, let's put 10,000 BTU over that constant, and that gives us 1 gallon a minute is going to equal 10,000 BTU. So that's kind of a good gauge to kind of get started if you're trying to understand if your system is designed for a 20-degree rise, you should be seeing about approximately 10,000 BTU for every gallon per minute. But again, that 10,000 on the bottom is a constant. So if we take that out and divide it up a little bit, actually the assumption in that constant was that we had a 20-degree rise and that the water had a certain density, specific gravity. There was no glycol in it. So if we kind of complicate that bottom constant a little bit and take out, you can see that there's the water temperature in and out, the differential of 20 degrees times a 500 constant. That's complicating a little bit more. If we understand the differential temperature in the system, you can determine BTU, you can determine flow. You need 2 of the 3 factors to kind of divvy up and do the math to understand either BTU that you're calculating or you're calculating for flow. So let's do an example of what that could look like on the next slide here. So let's problem solve with the sensible heat formula. So let's say we know we have 80,000 BTU output. Okay, the delta T, the differential temperature, we can calculate in the system, and we're calculating the supply water temperature of 160 degrees. Our return coming back is 148 degrees. So let's calculate for flow when we do that. So that's a 12-degree delta. So 12 degrees times the 500, that equals 6,000. And when you do the math on that, it's about 13 to 14 gallons per minute. It's 13.3 gallons per minute exactly. But remember, we have the 500, so there's still a constant in that 500 with the properties of water. When you plug in, and you're probably going to use software for this, you're going to plug in the temperature of the water, and you're going to plug in what kind of glycol do you have? Do you have ethylene glycol, propylene, and the percentage mix? And that can give you a more precise determination of what your flow would be. But it's a good kind of just get you close on calculating what your flow is. Something you can do in the field without having to use software. And just keep in mind that it's not going to give you precisely the exact flow because of that constant of the 500 that we weren't adding in the exact mix of based off temperature or the glycol. So, and that's a little bit on using the sensible heat formula for calculating that.
Okay, so now you picked your boiler, you designed your system, you've got the right pump selected. You called Brent, he helped you out. You made sure that you had everything set up correctly. But let's say you have the delta pressure reading on all these pumps, and you're still seeing it move around a little bit, depending on what's on and what's off in the system. We spent all that time, that hard work to make sure that the pumps are sized correctly, but kind of for static individual moments in the operation of the system. So if there is, the next topic that we'll talk about is how we make sure that each of these pumps can operate at what they were supposed to, because if they're piped improperly, there's potential that they're fighting each other all the time, or that one is inducing flow somewhere else when it shouldn't. So you've got, let's say all 4 of these pumps are sized perfectly for whatever they're doing out in the system. But now we have 4 different conditions of flow that's coming back through this high head loss boiler. And that's not really what we want either. We want to have that, exactly what the boiler manufacturer has, decided is going to be best for the specific delta T that you choose. So if we don't have no hydraulic separation, we don't have a happy ModCon boiler, we may be under or overflow there. These are smaller heat exchangers. The efficiency is better, but there's just not as much buffer capacity of the water inside of these systems. So it may be a gallon or less, where in the past that same BTU range of boiler may have been multiple gallons in a big cast iron heat exchanger, where there's just a little bit more time to buffer that change in flow. We don't have that luxury anymore. So we've got pumps in conflict. We don't have hydraulic separation anymore. We've got a range of velocities through that pipe. So as one pump is on, the feet per second coming back through the return is going to be different than when all 4 have combined powers at the same time. So this isn't going to work well. This is kind of a cut and paste. This used to be a cast iron boiler here. We've replaced that with a ModCon. We see it all the time, but know that these pumps aren't going to be happy anymore, or there's not really even a true way to size them anymore because they're in conflict. So what we could do instead, before that, I've got a chat question, so feel free to type an answer into the chat here and we'll read a couple of these off. And know that if you have a good question or answer for the crowd out there, we do have these special edition Perfect Loop Grundfos and Caleffi hats. You can't get these on the street. You can't get these at the mall. These are going to be just for people that came to the class or people that came to the webinar today and have good questions. So type in a question there. But what we want to know is, how do you know if an existing system has proper primary secondary piping? So if you did a cut and paste and aren't quite sure if that's exactly how it should be, what could you do to test that? I'll kind of keep an eye on the questions here if anybody wants to type one of those in. Okay, I'm seeing a couple come over. I'm going to jump to one way to do it. So if you have a flow meter somewhere in the system, you'd be able to just in this Caleffi quick setter, you'd be able to pull the pin and verify that, let's say it's this pump over here or the Grundfos on the left here. The Grundfos is going to give you the actual GPM on the screen with this alpha, which is kind of cool. You'd be able to verify that by pulling the pin. If it's a single speed pump that isn't going to give you a readout and you don't have that delta pressure gauge, then this would be a good addition that you'd be able to pull the pin and say, okay, right now, when none of the other zones are on, I've got 2 GPM. But when all of these other zones come on, this number changes. I now know that I don't have these pumps completely separated, that there is some flow that's being induced from zone 1 to zone 2, or from the boiler pump to zone 3 or something like that. So that's one way to at least figure out what is actually happening. Like Brent said, that regardless of what the previous doctor had prescribed here, if this was supposed to be a specific flow rate, but whatever has happened or whatever has changed, we're measuring a different flow than what we had in mind for the amount of BTUs we need to get out to that zone, we at least know how to pinpoint that and troubleshoot from there. So some pumps have that number in GPM right on the screen. If it's a single speed pump or a 3-speed pump, you'd have to measure the delta pressure across that and then use that conversion chart, which is fine. You can also just use a flow meter that'll tell you what is happening right there. So now I'm seeing a bunch of questions float back through. So we'll get hats to our favorite selections there. And then one of the questions is, shut off the primary boiler pump and see what happens there. So that's a good way to do it too, is that what's different with the boiler pump running and with it off. And that's going to tell us kind of the next piece. Do we have our wheels separated? So this is kind of an analogy that I like to use for this particular topic. So let's say, hydronics aside, let's just say we're talking about this gray dotted line box right here. This is a machine that you built. Either you engineered this or you're the mechanical contractor who came up with the fix here. You've got two different gears, and then this, I'll kind of describe the animation if it comes over a little choppy for some of the internet connections, but we've got this gear on the right that's spinning like mad, spinning really, really, really fast. The gear on the left is spinning slow. So is there a problem there? Do we have a machine that we would be proud of, or are we headed for some sort of mechanical failure? If we've got two gears that are, touching, that are in conflict and spinning at completely different speeds with not the right amount of teeth, and we're going to end up stripping one of those gears. If it were a simple machine, those gears are not going to work well. They're going to bind, they're going to strip. That machine's not going to last very long. So in a similar sense, instead of having rotations per minute, let's change the analogy to gallons per minute. So it's just still, a number of gallons now that's going around. If we do that, it's the same thing. We don't want the, let's say this is 10 GPM on the boiler side. We don't want that influenced or it flow induced by any of these other pumps on the system side. So if one of these pumps is on and now we have 12 GPM through the boiler, that's not what we want. We want to keep those gears separate. Another way I kind of explain it in the field too is that if you have a bicycle and it's on the ground and you try and spin one of the wheels, the back wheel, you're going to push that front wheel. If you pick the bicycle up and you're holding it in the air, you can spin the wheels at different speeds. That's what we want. We want the two wheels to be able to operate independently of each other. And one of the ways that we can do that is with the hydro separator, but I'll cover the three different kind of main categories of primary, secondary piping. So with the hydro separator, we now have two wheels that can spin independently. We'll go through kind of the mechanics of how these devices work, but we've got, let's say it's 20 GPM on the right side in this particular snapshot of the system and 10 GPM on the left side for the boiler. They're not pushing on each other. They're not inducing flow one way or the other. So the wheels can change, and the boiler, if it's a single speed, is happy, or whatever combination of those two things that occurs in any given moment in a system. We're ending up with no fighting or gear grinding, that we've separated those two wheels to operate independently. And that's what we want. We want to make sure that we're transferring heat across. We don't want to overdo it or underdo it in any part of the system, because the different zones are coming on and changing what's happening in the boiler side. We want to keep the boiler pump set up to make the boiler happy regardless of what happens anywhere else in the system. And honestly, that's part of the reason that some boiler manufacturers just build the pump right into their own cabinet now. They say, we don't want you to mess with this at all. We want the heat exchanger to get exactly that 10 GPM regardless of what you do in the system, and they build in their own primary, secondary components to make sure that that's protected in some sense. So that's kind of the inside of these two separators. We'll go through this in a little bit more detail too. So we've got three different flow scenarios in a primary, secondary system, and this could be a hydro separator or a buffer tank or closely spaced tees, which I'll talk about a little bit more in the next few slides. But in a perfect world, we have 10 GPM going through the boiler circulator over here, and we have exactly 10 GPM going out to the system. So if you were going to cut open that hydro separator and put just a little dot of blue food coloring right in the center here, it would just kind of hover in there as the top goes right across with the supply, comes back with the return. There's not really any mixing at that point. You just have the straight across the top, straight across the bottom. The chances of this happening are 0.000001 in any system where there are multiple pumps coming on and off. One of the kind of caveats here would be, let's say you are doing a snow melt system, and it's one fire tube boiler or something like that with low head loss across the heat exchanger, and then just a single on-off zone of snow melt. In that case, you could probably design a pump that would make both of those sides of the system happy at the same time. You would call that a full flow. you could do that without a hydro separator, because it's always going to be this scenario. It's always going to be 10 GPM out and 10 GPM back. That's the only thing that could happen. Anything that's broken down into zones, or any time that you wouldn't be able to make both, for the feet of head that you need and the flow rate that you need, both the system and the boiler side happy, that's when primary secondary comes into play. And that's going to be the vast majority of systems that are out there, especially existing systems or anything that's zoned. So sometimes the scenario 2 here would be that the primary is spinning a little bit faster. So the left side is spinning a little bit faster than the right. So let's say in GPM, that's 10 GPM, but we only have a need for 5 over here. So there's only 5 GPM spinning with the system circulator. That means that that 5 GPM is just going to go right back to where it came from, right back to the boiler. So we've kept the boiler happy with its 10 GPM. And then the system is just kind of going at the slower flow rate as it needs to. In that case, your little drop of food coloring in the center there is going to go right back to the boiler, and you would see, this side of the loop start to incorporate some of that food coloring that wouldn't go out to the system there. So the third scenario is we have the boiler is going at 10 GPM, but we just had a bunch of new zones open in the building. So the variable speed pump on the right side of this scenario going out to the system has turned all the way up to 15 GPM. So now in that case, we've got 5 extra GPM that need to go right back out to the secondary circuit and not back to the boiler. We don't want to take the boiler up to 12, 15 GPM, because that's just not what it was designed for. And this, the examples that I'm using would be a single boiler, but it could be any mix of 10 zones on the system side and 4 boilers on the boiler side. We don't want to grind those gears by having either side dictate what flow rate happens to go through the boiler or through the the radiant system or the cast iron radiators, whatever may be happening on the system side. So the 3 different flavors of primary secondary system that I'll cover a little bit more. The most common, kind of most widespread, would be closely spaced tees. So this is something that an argument that I like to have is that you could say this is the cheapest to buy the parts for. So you can buy 2 copper tees at the supply house for not that much money, even though the price of copper is up. That's going to be a very inexpensive way to do primary secondary system. From a part standpoint, you might even have them on your truck if you're a contractor, and it will work. So the part of the discussion here is that we'll talk about kind of my favorite way to do primary secondary piping, but this absolutely will work. The physics work here to separate the boiler and the system. So what we're designing for is kind of about 2 to 4 feet of velocity, kind of in this neighborhood of these T's here. And the big thing is that there's no pressure drop between those 2 T's. So this boiler circulator can operate without taking a big penalty of pressure drop before it could come back to the boiler return. So the way to ensure that we do that is to generously size these headers. So these headers need to be sized for all of these different pumps combined. They can operate at the same time, so we're not using 3/4 inch pipe to gather all these 3/4 inch branches. We wouldn't have what we would call generously sized headers at that point. So if we look a little bit closer at closely spaced tees, and this was something I had to reach out to find a friend to get kind of the best book answer for this. So I asked John Siegenthaler, what are we talking about when we say exactly closely spaced tees? Because if you have a 90 right on either side of these closely spaced tees, does that count? And the answer is you want at least 4 pipe diameters downstream of your closely spaced tees and a minimum of 6 upstream. So kind of like other components that you would put into a hydronic system, you don't necessarily want to have them right after a 90 or a T or something like that. You want to have a little bit of room to run on either side there. So the more distance, the better. But it starts to be a bigger assembly than you would think. So closely spaced tees, adding the pipe diameters upstream and downstream becomes a little bit longer than just the 2 components by themselves. And then the big one that comes up all the time is how close do these closely spaced tees need to be spaced? So I've seen the boiler books kind of evolve, the boiler manuals, where it used to be that you would see answers like no more than 12 inches, but not reference a pipe size. So the best answer is maximum of 4 pipe diameters apart. So if this is a 1-inch boiler line, you can't have that more than 4 inches away from the return here. So that's a hard one to do in the field sometimes, and we'll see closely spaced tees pretty loosely interpreted and sometimes pretty wildly interpreted, that the closely spaced tees are 18 inches apart with a 90 in the middle, and it's really not closely spaced anymore, and you're going to start to induce flow, and those gears are going to come back into conflict a little bit. So the best answer is 4 pipe diameters or less. As close as you can get it would be great, and that's to minimize the turbulence and helps prevent that those two pumps from fighting each other. So that's a good answer to go with. Another one that comes up all the time is we'll see closely spaced tees with a ball valve there. And then they'll say, well, but it's a full port ball valve. So first of all, the lay length is generally a little bit longer than 4 pipe diameters. There are some components that are the closely spaced tees with the valve built in the center, but you need to look at what the equivalent feet across that valve would be, because generally even a full port ball valve, it will have a flow penalty. It's not a straight length of pipe. Even going through a full port ball valve, which is just a marketing term meaning that it's the same diameter as the pipe, there is turbulence there. So a 4-inch spread of these lines with the ball valve in the middle may be closer to 6 or 8 inches apart if you account for the pressure drop going through that component. So this is helpful in some cases to put a ball valve here so you can close it and purge through the boiler and purge through the system, but there are other ways to do it. So this is another drawing from one of our hydronics issues. So you can still do that to purge through a line without putting that ball valve in the center there. That's usually a better way to go because you're not taking yourself out of that closely spaced tees, physics basically to put a ball valve in the center there. So now for the head loss calculation, we kind of went through the different math here, but this is what we'd like to see here is the result is that we've got 6 GPM going straight across, 4 GPM, exactly what we set up for our heat dissipation for that zone, needs 21,000 BTUs. If we start to induce a little bit of flow through there because these tees aren't closely spaced, we've changed our math a little bit here, and we're not going to have the delta T potentially that we were looking for, and we've started to affect what's going to happen in the system, which is not what we want. So this is an example from PSI in Colorado with Victaulic that they did a couple boilers. They've got 2 boilers on the floor here that have the short fat headers to combine them with the closely spaced tees, really as close as you can get with the Vic fittings there. So if they had a big valve in the center there, or if that was any further apart, they'd probably be out of their closely spaced arrangement. That's going to be as close as you can get it there. So that's a good example for that photo. The next one would be a buffer tank. So this is still primary, secondary design. This is going to be kind of like a hydro separator that I'll talk about in the next few slides. But as you're adding volume here to buffer out the cycles of the equipment. So this is something that as air to water heat pumps start to become more of the market share for equipment, they may say you will have a buffer tank. Like this is coming with it. We don't have the flexibility to modulate down really low. We want really long run times with these air to water heat pumps. This system will have a buffer tank. You have to have one for it to operate properly. So those are some cases that it's just required by the manufacturer. That's their kind of basis of design, is to have that buffer capacity. It still works perfectly as primary, secondary piping. So there's minimum restriction for the supply to come right back to the return here. You've got just this big lake of water right there that allows you to do primary, secondary. With the hydro separator, it's just supersized. So you're getting the additional kind of thermal battery effect of having that big volume there. So this is going to be really useful in a lot of cases. It may be something if you've got a bunch of microzones in system, that this last zone here, zone 5, is just through a towel rack or something really small like that. That's when a buffer tank is a great fit and is a good way to do primary secondary as well. This was a product that we used to have in the catalog when solar thermal was booming, and this would be kind of a similar setup that you could warm this up with solar and kind of sip off of this throughout the night when the sun's down. It gives you the ability to charge a thermal battery in your basement. One of the things that I think is always funny is in the conversation about Tesla batteries and where are we going to store all this electricity to smooth out the grid a little bit. You have one. You have a big thermal battery in your mechanical room today. So we can use these in system design to charge up a water heater off peak or a buffer tank and store some of that energy when the kilowatt hour rates are lower, that type of thing. So there are definitely advantages to buffer tanks. A downside would be the size and cost generally. So as I mentioned before, the least expensive way to do primary secondary based on cost would be 2 Ts. The most expensive way to do it would be an enormous buffer tank. And then kind of in between is the hydro separator. So a hydraulic separator, a low loss header, our particular brand with the magnet built in, we call it SEP4, all kind of synonyms for the same thing, primary secondary design. And essentially it's the smallest buffer tank that you could build. So it still maintains that primary secondary design, and the way that you size it, you could build one for yourself if you wanted to. Again, I would argue that the labor rate that it would take you to do it, you wouldn't make any money on it versus purchasing one. But if you wanted to, you could do a 1-inch connection coming into this hydro separator, and you could T-drill a 3-inch copper barrel that would be the center of it. And you can use that formula and get that spacing correct, and you could build your own hydro separator. The way that it works is that it's going to slow down the velocity coming in here. So if for some reason you had 9 feet per second coming into this hydro separator, which would be too fast for a hydronic system, but just as an example, it's going to slow down to 1 foot per second. So like that buffer tank, it hits that big volume of water and the velocity slows way down. So that's why we can separate air and dirt really well there. It's just based on the amount of volume and the velocity slowing down, we're going to be able to let that air separate up and the dirt separate down a little bit better. So this is when you put all these pieces together, it's going to be 2 connections for your air separator if you were to put that over here, 2 connections for your dirt separator, and then you've got the 4 connections there to put the unions on the hydro separator. So what I usually argue is that if you're looking at the cost of closely spaced tees versus a hydro separator in a catalog, you're going to say, well, the hydro separator is way too expensive. Why would I ever do that? It depends on your labor rate. So if you can buy an air separator and high quality air separator and dirt separator, as well as your tees, and then the amount of time that it takes to solder or press or whatever fitting type that you use to put all that together on site, and multiply those number of hours or minutes or days, depending on the pipe size, if you're going to weld something big. I always argue that the installed total cost of a hydro separator is really competitive. And if you're looking at kind of the tight COVID timeframes that we've had over the last couple years, this is a prefabricated thing that if it leaks for some reason, that's Caleffi's fault. That's not your fault. If there's a problem with this device, versus if you have an apprentice put together the system and a couple of their solder joints leak, that's kind of on you. You can't just break the unions and put in a new one from the supply house if there was that rare case that you'd have something leak right from the supplier, it was dropped by UPS or whatever the case would be. So that's why I argue the hydro separator is kind of setting all these components up for success. Smallest version of it, if you account for those 6 pipe diameters above and 4 above and 6 below for closely spaced tees, it's not even really that much physically bigger in a mechanical room too to combine all those components. So that's kind of my pitch for why hydro separator is a good marriage of these technologies and is the best kind of ready to go prefabricated version of closely spaced tees. So how do I size them? Not nearly as complex as some of the other pieces in our system. So once we know the GPM that we need for the boiler and for the secondary side, we pick the bigger number. So if the secondary side needs 230 GPM, the boiler pump has a different delta T. Maybe it's, you've got a bigger delta T on the boiler side than you do on the secondary side, something like that. You might have a pretty drastically different number there. You're gonna pick the bigger number and then pick the hydro separator that's going to cover that range. You can go as big as you want there. It just becomes a buffer tank. So if you need 230 GPM, you can select a 4-inch or bigger. If you select a 14-inch, our salesperson for the region is going to be really happy with you, and you're going to have a very big buffer tank. But you don't really improve any of the primary secondary piping. The 4-inch will cover you in this scenario. So this is another installation that I went to. This was Young Services probably 10 years ago in the Aspen area. And they put in this big hydro separator for the whole building. They've got 4 different boiler pumps coming on and off here. On the system side, they've got 2 different ECM pumps serving kind of the 2 different pieces of the building, east and west, or however they set that up. And the one hydro separator there has separated all of these wheels. So we've got 4 different pumps that could come on here through these short fat headers. And then we've got any infinite number of GPM through the building, and neither of those fight each other. So we've got the boiler side is happy. They're keeping all these floor mounted boilers exactly where they need to be on their flow curves without having any of this variable speed, velocity, flow rate affected at all. And that's kind of the best case scenario in a small footprint. So we've got the air and dirt separation and then magnetic as well now with the devices built into that small package. So we're going to do a poll for this next section, and then we'll bring Brent back in to kind of talk about zoning. So let me launch this poll. So the question is, while this loads up here, without any more background, there are many ifs and buts with this topic, but do you prefer zoning with pumps or with valves? And we'll, I'm sure that somewhere in between, but you have to pick one. You have to pick a camp today and say it's pumps or valves is your favorite. So we'll give this a couple more seconds here, and we'll see what the audience favorite is. Okay, I'm gonna go ahead and close it and share the results here. So you could probably have guessed that it's pretty close to right down the middle. We've got 52% of the audience is saying pumps, 48% is saying valves. We'll see that number change depending on where we are in the country as well. There are some places that they like zoning with pumps all the time, and there are some places that zoning with pumps isn't really the case. Does that surprise you, Brent, or is that kind of what you thought was going to happen?
Not at all. No, okay. I was kind of laughing here when I saw the results.
Yeah, so we've got a lot of data now to kind of prove that it is a split decision, which I don't know if that's helpful or not, but at least kind of gauges the audience today. So with zoning with pumps or with valves, one of the things that we can kind of start with here is understanding what type of system that we're working with here. So Brent, do you want to kind of start the conversation?
Sure,
here?
exactly. So if you're in the person that likes to use zone valves, the 2-way valves for your zoning, obviously you're in good company. Half the people do the same thing. But there's some things to watch out for when you do that when you're zoning. Obviously, if those were pumps where the 2-way valves are, we would look at each pump loop separately. We account for the friction loss of each of the loop, and we just look only at that loop one by one to size each of the pumps. In this scenario, the pump is not only doing the common piping, but it's also having to accommodate for all the zones. So all the flow added up for each zone would be in the calculation of your target flow for that pump. However, for the individual zones, one thing we don't want to do is take the friction loss for each individual zone and add them together. We're going to have a lot of extra over calculating the friction head loss that the pump needs to do. So because they're in parallel, all we need to do is figure out which zone has the highest pressure drop, and we just add that zone to the overall pressure drop calculation. So again, we'd look at the common loop of all the pressure drop at the max flow for the common loop of the bigger pipe, and then we just add onto that the zone that has the highest pressure drop. So that's kind of a thing to watch out for when we're accounting for friction loss to size the pump.
The things that you mentioned before too is that if it's all the same size, then it's probably the furthest away. But what if the second zone is, half-inch pipe, and then the rest of them are 1-inch pipe or something like that? So that comes into play too, that it's going to be the worst case scenario, not necessarily just the physically furthest away from the boiler loop that you need to account for. And then
Exactly.
one of the things that I'll mention too, that this is usually something that one of the listeners that rarely misses Coffee with Caleffi, Drew Gillette, always brings up, is that we don't want extra components that are just parasitic to the pump. So if we're using electricity to overdo it and then we're throttling it back down with a component, there are cases that we want to do that to balance out a building. There are some places to do that, but as far as just having too much pump and having to push right back through a spring to come back to the boiler, that is something that will make this system work and can be adjusted, and you can go with the fixed speed pump and kind of dial it in. But it is something that you're using electricity to just push against the resistance that you're creating that's not going out to the system, and you're going to take hot water right back to the return of the boiler, and you're going to cause it to short cycle there.
Right, and Max, don't forget that system setup with the differential pressure bypass valve with a fixed speed pump, that was developed in a time where you didn't have variable speed circulators
Yep.
at an affordable range, for this smallest size. So it was a solution developed for fixed speed pumps.
And it's still, it's a way to fix a problem sometimes that, we are over pressurized for these zone valves, and there's even, if it's wildly oversized, you probably need to resize the pump would be the first step. But there are some cases that, perfectly sized for the flow rate that we need through the boiler and through the worst case scenario zone, if that's zone 2 or 4 or whatever, that it's the right size. But then, like you talked about before, you open and close those different zones and you're at a different point on that curve. And maybe there are some cases that we are just going to start pushing a zone valve open and sending flow to a zone that's closed. We don't want that, so you can fix it with the differential bypass valve, but kind of talk about another way to do it as well. So a couple other questions that I like to ask at the start of any sort of zoning question that we get, if it's, should I use zone valves or zone pumps for this project? What would you define as a zone? If they say, well, it's just one big zone of snow melt, okay, well that seems like a great fit for a pump, and maybe even a full flow single pump that you could size up to fit everything. If they say, oh, we've got 27 zones, and one of the zones is, like I said before, a towel rack that 500 BTU per hour towel rack or something like that. That's going to be a very, very, very small individual thermostat bringing that on. That's something that a valve is going to be, probably a good fit there. And then we would have maybe one variable speed pump, kind of like the example that we've got here from American Plumbing, Heating, and Solar, where they've got an ECM pump that's going to do a lot of small zones throughout this building. That's a good way to do it. Do you have thermostats in each zone? Otherwise, you probably don't need the extra electrical energy to open 4 zones for 4 loops of a manifold that are all going to the same big living room. That would be a little overkill. You may break that up with just a 4-port manifold and a motorized zone valve or something like that instead. And then, are you over or under zoned, which is a very hard question to ask. That's something that usually you would want to check out with your heat emitter of choice too. If it were radiant, you could say, hey, can we combine zone 1 and zone 2 and end up with just a little bit more realistic curve that maybe we individually pump that brings us to some sort of more high run pump instead of some weird tiny flow rate pump that is going to be a special order thing. Because Grundfos has pumps all over the world that you could probably find exactly the pump that you were looking for. It's not going to be on the shelf anywhere. So could we combine zone 1 and 2 and find a pump that's going to be a good fit for that? Or is an ECM pump going to be able to kind of adapt to a lot of these different things? So as far as a fixed speed circulator, we've talked about this a lot, but we can kind of recap a couple of these things if you want to grab this one, Brent, and then we'll move on to another option.
Sure. So you know, zoning with a fixed speed circulator, one of the challenges without the differential pressure bypass is we could deadhead and we deadhead or shut off head. It's a situation we don't want to be in. I think Max, you mentioned that we could be pushing, you know, without that differential pressure bypass valve, we could be pushing open a zone valve, and that's not good for the system. So as far as this type of setup, we're spending extra energy to do this, and we're to be uh, bypassing the water, and we're actually short cycling the equipment because the BTUs have nowhere to go. It's maybe just one zone that's open, and we're bypassing, so we're bringing back higher temperatures to the equipment.
And then from the, you know, since we make the differential pressure bypass valves, that's not something that you just look at a chart and say, okay, we're going to set this to number 4 because we have 4 zone valves or something like that. That is a process that you have to stand there with, you know, it's kind of an old school thing. You stand there with your hand on the pipe and you feel when it gets warm, and then you adjust accordingly based on the number of zones that are open or closed to make sure that it's not always open, that it's not always the path of least resistance. We want it to just open up when we have, you know, 3 of 4 zones closed or something like that to avoid that deadhead, but not before that. And that's what's you know, a little tricky is that if we have it, you know, the spring tension is too loose, we're just going to short cycle our boiler all the time, and we're not going to allow flow to go out to those last zones. You could end up with a cold, you know, highest head loss zone at some point if your pressure differential bypass valve is set up wrong. And again, it's, you know, it's wasted energy to some extent. Okay, so here
And
are
then
2 different curves.
yeah, so of course, when we have all the zones open, that's going to look like the system curve, the blue one on the far right, and that's our design duty point, and that's what we're sizing for, and might have really good efficiency there. But as soon as zone valves start shutting off, it's going to create different system curves. You know, it could be like the scenario in the middle or the one on the far left with just one zone being open and calling. So you could size a pump for a system that is great at design when all are open, but in some of those low demand, low flow situations, you could be operating way to the left of the curve at a higher pressure situation, and that's where we could be back to pushing open a zone valve um, when we don't want to be. So that's kind of the things to watch out for with a zone valve system. And I think this is where you get into you know, if you can put in a variable speed pump in this type of situation, instead of increasing your pressure at low demand, you'll just keep the same pressure the entire time. So you're designing where that the 3 zones on the far right or all zones on system curve. You're designing for that point. That's the max pressure you need, and then we just stay at that same pressure throughout the demand as zone valves open and close.
Or you pay somebody to sit in the mechanical room and say, okay, if 3 zones are on, we're gonna go with speed 3. And if
Yeah.
only 2 zones are on,
Yeah.
we're gonna, you know,
Change
flip
the
the
knob as
switch.
conditions
Yeah.
change. Yeah.
We don't want that.
Exactly.
We don't want you to have to do that.
Yep.
Okay, so now let's say instead we're going to use an ECM circulator. You know, what are some things that change about our simple system here?
Right. So at this point, a variable speed circulator, it's going to sense an increase in pressure as valves close or a decrease in pressure as valves open and there's a call for heat. And it's going to adjust the speed based off of the pressure. And so that's where we have programming built in that can basically modify the flow for that system. So um, one of the things is that, you know, there's extra cost for the variable speed circulator when you do that, but you take out the cost of the differential pressure bypass. Um, you have the option that you can just give demand, but now we're not flowing back anything except for the zones that are open. So that maybe could cause some issues.
And you know, if we've selected the CV of the zone valve for, you know, to fit with the differential pressure that we're creating from the ECM pump, we're not going to blow zones open as, you know, one zone closes or whatever. It's just going to kind of iron out that potential issue where we're overheating zones. I remember when these pumps first came out, I was all excited about the energy efficiency piece of it. And I would explain that at the counter. I worked at Able Distributors at the time, and I would get kind of blank stares and be like, yeah, it's more expensive. And then every once in a while, I would get to the point where I said, well, and it's not going to force open the zone valves anymore. And I would see people from a service standpoint kind of perk up and be like, oh, I've got a couple jobs that are nightmares because I can't get the right
Oh,
speed
that's what's
or
happening.
pump size. So
Oh,
yeah, that's what's going on. So now they have a pump that's just not going to create that discomfort problem, just because it's going to modulate up and down. It's going to be the person in the mechanical room to change from speed 1 to speed 3 without any input there, which is what we want.
and the
So
fixed speed circulators are good for that max design point, and you can design for that area, but you have different system curves and different system conditions with the zone valves that you may not be at a good operating point with fixed speed. With variable speed, you have more of an option that you can be in a better spot running a more efficient point.
And then with this particular drawing, a downside is if you just had a cast iron boiler piped like this without primary, secondary piping, is if we're down to just a single loop that we've slowed all the way down to 2 GPM, that's not going to keep that boiler happy for very long. So that's the case that ECM is going to be a great fit for, if we cut this in half for the system side here, but you'd want to put in primary, secondary, and put in a boiler pump that may be a fixed speed for the single boiler there, and then we keep both sides happy. Okay, so here's another kind of a chart to go through the details here.
Yep, and this just describes, what a constant pressure scenario would look like graphically. So you can see, again, our system curves overlaid on a pump curve. So it's a little bit more busy of a curve, but we do show, there's 4 different system curves. So 4 different system scenarios with combinations of valves being open and closed. And then here we actually have RPM, the speed, so max speed 100%, then 90%, 80, 70, 60% speed curves shown on there. So if all zones are open, we're operating at that pressure scenario at 100% speed. And we slow down to maybe around 90% speed for that other system curve scenario. And we slow down a little bit more incrementally with constant pressure. So it looks like in a low demand situation, one zone being open, we're maybe running a little bit over 80% speed, all just to accommodate that, hey, our max design for flow and head, we don't need to output more pressure as system conditions change. We'll just keep that as the max pressure no matter the demand. And we get power savings when we do that, when we slow down our pump.
And now you're not, at this, if we were at this point on the curve with a single, as the zones are opening and closing, this is where you could potentially push that zone valve open. So we've just kind of stayed below that number, which is great. Okay, so some other pros and cons of zoning with pumps. One that we hear a lot is redundancy. So if one of these pumps, if somebody shorts it out or whatever, there's an issue with that pump, we've lost zone 1 only versus losing zones 1 through 5. So redundancy can be really important if you've got critical zones. So you want to make sure that if one of these pumps goes down for any reason, that the other 4 are still good to go. That is definitely a legitimate, concern and way to do it. It's easy to size and balance these because you just say this is for this zone of radiant that we can pull the report and say we need exactly this flow, exactly this feet ahead. That is going to be just what we need. You can split those apart instead of having to find what the worst case scenario is and then find something that's going to work for all of them. Troubleshooting is easy. You can say, is this zone overheating or underheating because of what's happening with this pump? Are we inducing flow or not? You can do it that way. The downside is that it's going to be more electrical energy. Even if these were all ECM pumps, it's going to be more cost for not just the purchase price of the pumps, but also the isolation valves and the flanges or welding together, whatever you're doing on a bigger scale, and the labor to do that. So those are kind of the pros and cons. Anything else that you would add there? And I'm sure that there are a million more.
Well, the troubleshooting piece is big. So remote troubleshooting. So there's some contractors that that they can sit at home, take the call from the customer, and say, okay, well, go down in your mechanic room. Do you how many lights do you see on? Sometimes there's a light output on the pumps, and they can, okay, so I think what we have is a pump problem for your bedroom because your bedroom's not heating up and it seems like that pump is down. So they know what to do before they get to the job. So I think remote troubleshooting is what some contractors like to use the zoning for.
Yeah, and I think that especially with the ECM pump that you guys have that has the number GPM right on it, you can say, well,
Correct.
does it say 0 or does it say 2?
Correct.
Same
Yep,
thing that you
exactly.
would do with a flow meter, but that can really simplify it, or you can see it, come to life as all the zones open and it turns up or whatever the case may be. Okay, so we're going to switch over to some ECM specific stuff here that I'll have Brent kind of walk us through.
Yeah, so speed control pumps, we hear the word ECM a lot, and what does that mean? And okay, electronically commutated motors. Okay, what does that really tell you? We like to say in the Grundfos world just what it is, which it's a permanently magnetized synchronous motor. So what does that mean? So the rotor, the interior rotating rotor, its speed is going to be synchronized with the magnetic fields of the outside rotor, which you can, or I'm sorry, stator that you can see the coils of there. So it's synchronous with the input power. And why I kind of wanted to put this picture on here and why speed control pumps, because most installers know that they cost a little bit more. You do get a heck of a lot more out of it. But you can just see from a basic level, there's a control board in there. And adding control boards, and extra pieces and parts and permanently magnetized rotor, it's extra cost for that. And so we need a control board so we can intelligently control the speed uh, of the pump, and so that we can add extra things in if we want to. So we can add as little or as much programming as we want into these style circulators. That we could have a basic version, we could have something more advanced that it can sense what's going on in the system. You need a circuit board to do those things. And what it does is it helps us adapt to loops better. So we talked about having the low, medium, and high speed with some of our other circulator models. Well, with these, we have even more control options to adapt to different types of loops. So the pump behaves in different ways depending on the application. And as you alluded to, Max, with the circulators we've had in the past with our alpha version, flow is a readout. So you can get a quick, okay, well, what's the flow of the system, and even what's the watts right now, and it just scrolls between the two measurements. So you can use it as a diagnostic tool right then and there, whether it's commissioning or later on when you're trying to troubleshoot. You can use that as a data point as you're trying to understand what's happening in the system. And also reporting. So it can be upfront commissioning, or it can be later on when you're servicing the equipment. You can download through Grundfos Go through an app. You can download the report of all the settings, where you had it, and just keep that on file as you would other equipment when you do startup. So there's a lot of things for the installer that can help justify the upfront cost. We can maybe do balancing a little bit faster because we know that flow, and we can adapt a lot faster, and there's a lot less guesswork as well. So an installer might want to consider. And then as far as the end users, as far as the homeowners, there's lots of reasons why they'd want to have them. They don't need to understand all the technology. They just want to know, am I comfortable, and am I saving energy? And I don't want to hear the thing run. So you get all those benefits out of variable speed, because with some of the fixed speed, you could be put in an operation and something happened with the design or the loop, and maybe it's creating too much velocity and it's creating velocity noise. Well, you can kind of fix that by turning down the speed, setting to a different control mode, and we don't have to hear it run like that. And then also the energy savings just by having that permanently magnetized rotor. That's one, and then reducing the speed. We get lots of energy savings from that in the pump, but there's also energy savings when we're helping optimize the delivering of BTUs to a system. Instead of on-off short cycles with the equipment, we can kind of match, if it's modulating condensing equipment or heat pump equipment, we can kind of match the flows to what the differential temperature needs to be for the equipment. So there's lots of things that we can do, and that all equals energy savings. So let's go on to the next slide here. Do you have something else on that?
The perfect loop is the laziest way to get energy throughout the building too. There's no perfect loop isn't, 4 times the pump size. It's going to be noisy, and comfort's going to suffer, and it's going to use too much energy. Perfect loop is the least amount of wire-to-wire energy to keep that pump getting the entire building happy or the boiler happy.
And we can design for the most efficient pumps, that's great, but as long as it's complementing the heating system that it's connected with, that's the most important thing. So one of the things that we like to mention here, when you have a variable speed pump and ECM pump, there is a relationship between the change in speed with flow, with head, with power, and this is a lot of times where people say, but you know, a change in speed, and you reduce the speed, you get a lot of energy savings, and that's true. So you can see from 100% speed, we change down to 80% speed, so a 20% reduction, you get a corresponding kind of linear relationship with the change in flow. So if it was 100 gallons a minute at 100% RPM, we go down to 80% of that speed, we're going to get 80 gallons a minute. But when we look at the friction head loss, it's more of a quadratic equation there for that. It's not a linear relationship now, cubed relationship with power. So yes, a ton of energy saved down to 80% speed of the max speed. We could be almost 50% of the power used in that scenario. But don't forget about the friction head, that we're looking at around 35% less head needed. So just think again about our max design point, our duty point, and then as soon as conditions change in a system and we need less flow, our friction head needed, or a differential pressure that the pump really needs to do, is less than the max head. So keep that in mind when we're talking about control modes of you know, changing flow, changing demand. We typically need less friction head. So let's go on to the next slide, and we can see what that means as far as some of the control modes. So this is a really exciting thing for us. Before I get into the control modes and the curves, we are introducing new ECM models. So we're really excited to offer a new platform for our customers that, you know, our Alpha, you know, we released that about 10 years ago without offering new ECM options over the years. So this is our first release and a really big announcement with our UPSE model. So it's a basic version of an ECM pump, and you can see on the green dots there, there's 3 different control modes, and I'll just tell you, it says zone pump situation, it says zone valve situation, and TRV, thermostatic radiator valve situation. So within each of those, so right now it's on zone pump, there's 3 different settings for zone pump. And zone pump, that's just a constant curve or a fixed speed setting. So if we wanted to go into a zone valve situation, we can toggle by hitting the right arrow, and there would be 3 constant pressure settings for the zone valve scenario. So if you want to click through a little bit more, so that would be an example. That's the lowest zone pump curve. So instead of just the one pump curve, we have several different options. If you had a duty point in that green zone and it was a zone pump, that could be a good setting. If we scroll through again, it's going to go to the proportional pressure. So that's actually the TRV setting that we actually have modulating demand, that it's going to, when we have less demand, it's going to output less differential pressure. As I was mentioning with the affinity laws, in these situations where you have less flow, you need a lot less differential pressure. So there's 3 different proportional pressure modes with that TRV setting. And then finally, the constant pressure that we've kind of already talked about. And again, looking at that, it's kind of busy, control modes for different situations, for different loops. And if you have a duty point in there that's touching one of those areas, you have lots of options to select from, whether it's constant pressure, a constant curve or constant speed, or the proportional pressure modes. So lots of options with this new UPSE. It is a ECM circulator for the heating market. So let's talk a little bit more about it since it's a new product, and why is it so different than what we've had in the past. So there's more things built into it. One of them, I guess on the picture, it's showing you on the left there, is there's the new tabs and easier to wire than what we've had in the past. So it comes with that kind of Molex piece in the box, and you put the wires through on the bottom, and you basically just push them up in, pull the tabs down, and then you press the whole piece into the Super Seal Molex piece inside the terminal box. So it's a lot easier setup than we've had in the past. So one of the features that we have listed there is self-venting of the pump. So this is a little bit of air that can get in the rotor can, that it's a feature that it's an always-on type of feature. So if there's a little bit of air in the rotor can, it's designed to get the air out, and it can do it in any of the speed settings. If it happens to be in the highest speed setting, the air is going to get out quicker. So we do recommend an initial startup to put it in the max speed, and it'll take about 15 minutes for any air to get out of the rotor can. So that's a pretty exciting feature that we have for this new platform, is self-venting of the pump in the rotor can. So dry run protection is another piece. So, we just want to reduce the amount of times that pumps failing based off of a dry run situation, or air being in the pump. So that's why we have that built in with dry run. And there's different control modes. So it's a built-in dry run programming sequence that it will be slightly different based on whether it's commissioning initial startup situation versus a normal run operation. It's kind of different programming for each. So that's built into this pump. And what's the next feature we have listed there, Max? Best efficiency, that's a good point. So we're going to get that with the TRV, the proportional pressure control mode setting. We have the best efficiency in this smaller circulator range in the industry. And we're showing you the wiring there. So just some basic things. That's a really good upgrade to what we've had with our past platform. And then the next slide, I think we just talk about digital next. That this is kind of the beginning of what we can do from a digital perspective. We can do a lot with the hydraulic efficiency, and we've gone a long ways. But as we tweak and as we add and as we upgrade our offering for our customers, it's a lot of it's in the digital space, and it's adapting to loops, and it's auto adapt, and it's these kinds of features built in to adapt to the application. So we're just kind of scratching the surface of what we can do with circulators from a digital perspective. Connected pumps, connected equipment, connected smart homes. That's the future that we're preparing for with this digital next and digital product offering. And we say, that these pumps are now born connected, that we're ready for the future with digitally enabled pumps. So we're pretty excited about what's to come. So keep your eyes on Grundfos in the future here. ASHRAE is going to be really exciting for us this year. So really excited about this new platform.
And you're going to make us wait till ASHRAE.
We're going to make you wait,
details, right? Yeah.
This picture looks a little bit different than the last picture. But yeah, we'll make you wait just a little bit. So.
Okay. And then one last technical thing to cover as we get to the end of the presentation, and there's just a much bigger discussion to have here, is a good coalescing media for an air and dirt separator is going to keep these pumps running at the design capacity and the system as a general statement too. So something like our Dirt Mag Pro, we want to catch that magnetite before it gets back to Brent's nice ECM pump. We don't want that ferrous material building up inside of the pump, even though they've got more protections to figure out that the pump's slowing down and it doesn't like it. We just don't want to get it to that magnet to start with. So a bigger magnet upstream of that with the Dirt Mag Pro, all the way through the flanged version is going to help protect those components. And then same thing with air in the system to make sure that even though the pump's self-venting, there's just a lot of work to keep it from even getting to the pump in the first place on the hot outlet of the boiler, being the best location there. So that's kind of the wrap up of this. This is a huge topic. This is something that we went from a 4-hour in-person presentation to try and bring it back down to 90 minutes, but I'll kind of get to the wrap up slide here. This is what we talked about today, since we're just past the 90-minute mark. And we'll do a thank you to Brent for being our guest presenter today. Really helpful to have another ally in the industry kind of explain, kind of back to the initial concept. How do we not point fingers and say that Grundfos will figure it out, or Caleffi will balance it out, or whatever, but how do we kind of know how to combine these two things and make sure that everything's working well? And that's kind of the goal of this series. So I'll go through the last couple slides here. If you have any technical questions, reach out to us by phone or by email. These are the human beings that'll get back to you if you have got any questions. Oh, we have Matt, we need to add. Got another person on the phones now too, who was a plumber before. You can listen to the guys on the podcast, talk about the usually things that they, are issues that come in that they talk about on the phones, and they figure out how to fix it, what went wrong, some anecdotes kind of along the way. This series by Cody Mack is really good if you've got, you want to talk about these same topics that we covered today, but just in 5 minutes instead of 90 minutes. This is a great series that we've got on YouTube. And yeah, tag us on social media. We love to see your job sites out in the field and kind of interact and give you kudos when we see something that looks great. And I know that the Grundfos team does a great job of that as well. So that's going to take us to the end of a shortened marathon version of the Perfect Loop. Thank you again to Brent and to Grundfos, and we'll see you next month with John Siegenthaler. Will be back in front of the class for air to slab heat pumps with Radiant. So thanks again. We'll see you soon, and we'll get some hats out to the good questions that we saw come through. So, all right, we'll see you next time.